Thanks a lot, everybody, for being here. I'm glad that I was actually able to make it here because, well, it's me we're talking about. So there's a very real chance that something could have gone horribly wrong. At least I went to the right California. So what I'm doing today is I wanted to give kind of a more mathematical introduction to quantum machine learning than is normally done in this. One of the reasons why is I recognize that we've got a diverse audience, and also I feel that often the more mathematical side of quantum machine learning is usually neglected in some of the discussions. And I feel that having a little bit more of an attempt to try to formalize a lot of what we want to do with quantum machine learning, I think is useful for kicking off a discussion amongst the many mathematical disciplines that are represented here. So this means that there's a very real chance that some of you might not, fully grok everything that's going up on my slide. So what I want you to do is interrupt me. Because for something like this, my view on it is I'd rather not get through all of my slides and have all of you walk away having learned at least one thing, rather than rush through all of my slides and people say, well, okay, that was an hour of my life I won't get back. All right? So please interrupt. And I have this wonderful magical stylus thingamabobber that allows me to treat this like a whiteboard talk. So I can write stuff here, quite literally, in fact. So what and why quantum machine learning? Well, quantum machine learning it comes about because of this simple expression. ML equals hype. Quantum computing equals hype. Therefore, QML equals hype squared. Okay? Wonderful. Congratulations. Now you know 50% of what you need to know to understand quantum machine learning. But there's a reason behind the hype squared that's going into it. At a fundamental level, what is a quantum computer? A quantum computer is a device that ends up giving you the ability to, this is, of course, a quantum computer. And actually, you can tell it's not quite a quantum computer because of the fact that it's not a black box. But in any case, what a quantum computer will do is it'll take some vector that is inside a space, a finite dimensional Hilbert space, which we can represent as a complex vector of dimension 2 to the n, and apply an arbitrary unitary transformation, UV, to it. Frequently, of course, for those of you who've seen it before, we'll use Dirac notation in order to be able to represent pure state vectors, okay, which all that ends up meaning is that it's a unit vector. Okay, so it allows us to be able to implement on just n qubits an exponentially large linear algebraic operation. So this opens up the possibility for us to be able to actually get exponential advantages for quantum computing. And that's one of the things that ended up getting people really excited, especially because many of the algorithms that we know and love in machine learning can actually be rewritten or rethought of as linear algebraic tasks. In particular, one of the ones that really ends up coming up is the simplest method that you could possibly think of for doing classification. Let's say I've got two different classes over here of data. And this is, for here, two components. Let's call this feature 1, and this would be feature 2. What we'd like to be able to determine is whether or not a input vector is in class 1 or it's in class 2. So what we would do in this case is we would do something like the following. We would find a separating hyperplane between these two classes and then determine which of the two sides of the separating hyperplane that we're on. In this case, finding the separating hyperplane can be rewritten as a least squares fit, which we can implement via linear algebraic operations that the quantum computer could carry out. Theoretically, exponentially faster than what you could do with conventional algorithms on a classical computer. So great, that's what really got people kind of excited about this, that a quantum computer can potentially offer huge speedups for these things. But after that, the situation started getting a little muddier inside the field. One of the reasons why is that it turns out being able to apply operations on an exponentially large space is necessary for a exponential quantum advantage, but it's not sufficient. Anybody know why it's not sufficient? Takers? Yeah.
Well, depending on the operation, it can be efficiently classically simulated.
Sure. And yeah.
Measurement.
Measurement is one thing that ends up coming in. It's subtle and it's complicated. And yeah, we do have to worry about how we extract information from our quantum computers. Because one of the things that's super annoying about these types of things is that here we have n qubits, and I promise I'll get past my title slide eventually. We have n qubits coming in here, and when we end up measuring this, we only end up getting n bits of information coming out the other side, no matter what we do. So this means that if we have an exponentially large vector that encodes all of our information, we only get to suck that information out through the thinnest of straws, because we only get n bits of information at a time for it. So the art of designing a good algorithm for this is incredibly subtle, because we've got to figure out what's the bare minimum things that we need to know and make sure we extract just that. So for example, if we're dealing with something like, say I wanted to do a large language model on a quantum computer, the number of neurons that you end up having inside these large language models is unofficially on the order of trillions. So that means that, if we translated it directly over, we'd have a vector space, of 2 to the trillion, or maybe even log log of a trillion if we do an amplitude encoding for it, which I'll get to later. But the problem is that even if we have that, then we'd be stuck getting log trillion bits of information back out, and we'd have to repeat that a huge number of times to do the same thing that the classical computer can do. So that is referred to as the output problem, which is a major a challenge for quantum machine learning. There's another major problem that ends up coming in. How do we load our training data in? So if we have to prepare some kind of state inside this immense vector space coming in. And in general, just from a counting argument, if you've got a 2 to the n dimensional space, you're going to need something like on the order of 2 to the n operations in order to specify every unique function that you can prepare on that. So that is known as the input problem, and you can be screwed for that too. Okay? So those are two of the big things, but there's a third way you can get screwed. The third way you can get screwed with this is you can actually have a classical dequantization of this. Here's why. Immense vector spaces are not a unique property to quantum mechanics. In fact, probability theory has the exact same thing. So for example, let's imagine that I have a coin, just a simple ordinary coin. My coin is distributed via a probability vector of say 1/2 heads, 1/2 tails. If I have 100 such coins, then what does my probability vector end up looking like? My probability vector would be, C goes to C tensor 100 equals 1/2 tensor 100, which is in it's a real vector dimension 2 to the 100. So what this ends up meaning is that actually ordinary probabilistic algorithms also take place in an immense vector space. So the question is, what are the right things that we need to put together in order to be able to find an advantage for machine learning for many of the tasks that we know and love? And furthermore, this begs an open question that we still don't really know, which is for classical machine learning, what are the killer applications? And at best, we've got polynomial advantages that we can end up rigorously proving. And we have exponential advantages for some contrived problems, but we don't have an exponential advantage that we can clearly point to for a classical task that is actually practical. So this is one of the big problems. So you might ask, all right, Nathan, you've hit us with a big negativity bomb right now. And yeah, that's one of the things, apart from not showing up to conferences, is what I'm known for. So but there's a reason why I continue to do work in this space. And the reason why is that there's actually a deeper question that belies all of this issue of speed up whatsoever. And that question is, what the heck does it even mean to learn in a quantum world? What are the right analogs of the classical machine learning tasks? And can we think of a particular, can understanding what learning ends up meaning in a quantum environment provide a deeper understanding of what the limitations of learning are in general, as well as what can it tell us about our ability to be able to learn from quantum systems themselves? And that is why I do this. Not so much because of the potential advantages that we can end up having for large language models. To be frank, I'm not sure they even exist. But what I don't know is, what does it mean for an electron to learn from another electron? That couldn't tell you. And quantum machine learning provides you a tool set for understanding this. So before I go on to the halfway point of my talk, which is slide 2, any questions? No? Yeah, this has all been crystal clear. I get it. Okay, cool. So let's move on. You see, it's a math talk. So one of the things is that, you see, you should have asked me questions. Now you're regretting it, aren't you? But the question is, what does it mean, really, at some level, to be able to learn or build a quantum machine learning algorithm? And what I wanted to do is I wanted to try to give my best shot at coming up with a kind of more formal definition of what it actually ends up meaning to have an algorithm that learns. The key thing is that to have an algorithm that learns, you have to have evidence that's coming in. And in order for it to be quantum, some part of that better be quantum. So from that perspective, the way that I view it is that a quantum machine learning algorithm, what it does at some level is it takes a bunch of bits that specify some initial conditions. Those could be weights for your model. They could represent some prior knowledge. They could represent whatever. Okay, so take some classical bits that you know and love and you shove that into your model. But it also ends up taking a set of density operators, which are quantum states. And you can think about these as because they're matrices, they can really just be thought of more broadly as linear operators mapping a finite dimensional space onto itself. So that's why I used like fancy notation up there for it. And so fundamentally, if you would like to be able to use this to be able to answer a decision problem. Of course, you can answer any question you want by composing enough decision problems together. So that's why I said, without loss of generality, let's think about a quantum machine learning algorithm is always implementing a Boolean function. Because for any more general function, we can always compose that as a series of Boolean functions. But that's basically it. Yes?
Nathan, since you like questions,
Well, we'll see if I still like questions after yours.
what's about the domain of that A? Do you want to specify it? Does it really have to be defined on all of these objects?
Well,
or can you have a guarantee that I only
fundamentally, we really actually only care about a subset of these operations. So we only actually end up caring about the definition of this function on valid quantum state operators, and actually, furthermore, only a subset of all potentially infinite-sized strings. Because let's face it, if I encoded my input as arbitrary length strings, there's a whole bunch of computational things that could happen. So yes, we only care really about this acting on some subset. But I didn't want to go into the details of specifying what exactly that valid subset is, other than saying that yes, the case of interest here is for proper quantum state operators, for the operators in LS.
So is the number M part of your data, or?
That's part of the inputs. So it specifies how many training examples that you end up getting from here. So each of these quantum states that's put in is part of your quantum data that you're using in order to be able to specify this particular function. And here, just for simplicity, I haven't separated the training and the evaluation of the function. I just considered merging it all together. So all of the training data, for example, all of your images that you think are secret in your Google Cloud, that would be stored here for a quantum machine learning task, okay? Especially those super secret pictures that you hope it never gets trained on, but you know, it probably still does. Yes?
So I'm generally curious, if we say without loss of generality, decision problems can describe a lot of things, but do you also think of generative learning here, so something for probability distribution? So this is a setting at the moment that you exclude from.
Oh, I'm going to talk about generative learning. Don't worry about that whatsoever. But at a high level, it's a question about how we're thinking about quantum generative training. You could end up thinking about such an algorithm as, for quantum generative training, as being end-to-end. No matter what, we're going to have to extract some information out of the quantum states that are being generated. And we could always view that information extraction procedure as a Boolean function. But zooming in a little bit more, it's less helpful to think about, I agree, the generation process in terms of this definition. But I really wanted to try to come up with a kind of an encapsulating formalism that would describe everything. Now, one of the big things that I think is really important when you're thinking about quantum algorithms in general is that no quantum algorithm, no complete quantum algorithm should ever output a quantum state, okay? Ever. One of the reasons why this, I think, is so important is actually because of a programming competition that ended up coming up years ago. And this is, again, one of Nathan's patented digressions. But I swear, this one's important. So there was a competition years ago to see which programming language is fastest, because you know how programmer bros are when they get together. They're like, oh yeah, my language is faster or better than yours. Oh yeah, no way, mine is way better than yours. So they decided to settle this once and for all.
There's a question.
Yeah.
That's cute. So, okay, how do we do it? Hello.
Well, it's the person who just asked the question. You should unmute yourself and ask the question.
Okay.
Oh, sorry. Yeah, my Zoom was glitching out. I was wondering. So when you say in quantum algorithm shouldn't output a quantum state, what about stuff like HHL? Because I know that you output like a quantum state, right?
Exactly. There's this beautiful, wonderful article I recommend that you read called "Read the Fine Print" by Scott Aronson. That ends up talking about the dangers of thinking about HHL as an end-to-end algorithm that just outputs a quantum state. Because in many cases, some of the exponential costs that you would end up getting from trying to learn what the output vector is end up getting glossed over with that. And furthermore, actually, this is the main point of my story. So let me get back to my story, and hopefully my story will answer your question. So anyways, programmer bros are sitting around trying to figure out what's the best thing. And this is how their program, the test, ended up working. The test ended up working as follows. What it did is it came up with a complicated linear algebraic operation that they wanted to carry out. And then upon doing that, the program was to exit, and then the timestamp from when the program terminated would determine which one's fastest. And what ended up coming out from this is a bunch of things that weren't surprising. Fortran ran amazingly well. C, C++ also ran really well. Pure Python, without calling any LAPACK or anything like that, sucked. But the best language shocked everybody. The best language, which beat all of them by a huge margin, was Haskell. Now, that's interesting, because Haskell does not have a reputation for being a fast programming language. But it does do one thing very differently. What it does is it lazily evaluates functions. So it went through and said, oh, you're doing this big linear algebraic operation, but the output is never called. I don't need to do anything. I just exit immediately. This is why we should not think of an end-to-end algorithm as just outputting a quantum state. Because if you output a quantum state, you do not learn anything from it. You only learn things from measuring that quantum state. And so for that reason, you lose out on a lot of the information, in some cases the complexity of the algorithm, just by doing that. Because if you don't learn anything, well, guess what? I can do, you're not learning anything right now. And, there's plenty of ways that you can come up with stupid algorithms that would be able to emulate you not learning things much faster than this current algorithm. Yes?
So what if the quantum machine learning algorithm is a part of a broader workflow, but the output is fed into another quantum algorithm?
Yeah, so then the idea basically would be at the end, what I'm trying to capture is the entire workflow, going all the way from state preparation through to the final measurement in the end. So it's the entire workflow, and I'm assuming that you want to get information out, so we don't have the Haskell problem. Yes?
Hey, Harry. The output of the quantum algorithm is going to be a random variable, right? How do you define the function out of it?
How do you design a function that does this?
No, sorry. In your definition?
Yeah.
Like you're basically saying let A be a function that describes the output of an algorithm, where like you have a bunch of linear operators specify a quantum circuit and measurement and all this. The output of that in the quantum computation, as far as I understand, is going to be a random variable. How can I get a deterministic function out of it?
Oh, I'm not saying this is necessarily a deterministic function. What I'm just talking about is the domain and range of this. So every single time you run this, you're going to get a bit coming back out of it. And that bit may be probabilistically determined. In fact, generically, it will be, right? But the key point is that, yeah, there's just always this information coming out. Okay, any other questions? But I guess the key point here is, from what I mean for quantum machine learning, there's one part about this that is vitally important. The part that's vitally important is this part over here, that there exists some kind of a quantum input that ends up going into the algorithm, and that the output is a function of those of that quantum data that's coming in. Oh yeah, and there's some other conditions and stuff that is needed. One of the big things is, in order for this to be actually meaningfully quantum, we have to ensure that it can't be dequantized. So we can't convert it into some randomized algorithm that could be doing the same thing. And these additional caveats on top of that come up with some restrictions that stop the most obvious of flaws, where you could come up with some randomized algorithm and say, hey, it's quantum because it satisfies all of your requirements. Because you can, after all, always represent a classical probability distribution as a density operator and satisfy this requirement. So I wanted to make sure that there were some additional caveats that were put in kind of in a DiVincenzo criteria-ish way in order to be able to rule out randomized algorithms as being quantum machine learning algorithms. So this is what I mean by quantum machine learning. And there's questions about how you would end up doing this. So in practice, there's a question about how you would end up loading things in. So for example, let's consider the most important thing you can ever possibly load in from the perspective of machine learning, which is these guys, the little fangs here, and that. Maybe it's got some fur. You guys all know what this is, right?
I said it.
What?
I said it.
Yeah, oh, you did? I didn't hear you. Cat. It's totally a cat, right? Good. Thank you. I ended up getting all sorts of gold stars in grade 1 art. So, I just wanted to show it to you. Man, that is nightmare incarnate. But in any case, the training data that we end up getting for images for machine learning algorithms are disproportionately cats. One of the main reasons is because of the fact that often they're trained with still images from YouTube videos, which are, 30% by mass cats. So you believe it or not, most image recognition algorithms do a phenomenal job of identifying cats and humans, because those are the two things apparently we're most interested in. But in any case, the simplest encoding that we could do if we wanted to load this image into a quantum computer would be to take the binary representation of this image and then map each of these bits over to a qubit. Okay? Nice thing about it is that this is 100% flexible. We can do anything with this that we can do with ordinary machine learning. The downside with it is we need an absolute crap ton of qubits. So if I wanted to do something like this for a large language model, then number of qubits that I would roughly need in order to be able to specify the entire network would be about 1 trillion qubits, okay? Which is a little bit of a bummer, because at present, where we're at right now is roughly speaking here. Okay? Which isn't actually all that far away in a log plot. But apart from that, that's a story that only funding agencies would love. So this is why very few people actually want to do this type of an encoding. It's the most flexible encoding. After all, you can do anything you could do with ordinary machine learning. You can clone images to your heart's content because they're just binary bit strings. No cloning, the no cloning theorem does not apply to bit strings. But unfortunately, you cannot fit anything like this into an existing quantum computer. On the other hand, if we use the next type of encoding, amplitude encoding, then we actually can. The reason why is that what we do is we take advantage of the fact that these vectors lie inside an exponentially large Hilbert space. Yes, do you have a question? Nope? Okay, cool. So the basic idea is, let's say that we had this vector, 1, 2, 3, 4, for our training data that we wanted to encode in our quantum computer. The natural way that we would end up doing this is we would just take that vector and write it as a unit vector, which is then going to be a valid quantum state. So I would write it in the following way. Okay? So divided by root 30. I don't know why I wrote that. There's probably some reason. But okay. So the moral of the story is that that's what we end up doing. Oh, yeah, okay, this is probably what I was doing. So this probably should be like a root 2 over here, maybe, oh, no, yeah. Yeah, it should be a 2, 3, 4, yeah, exactly. Cool. Now you're getting exposed to Nathan's slides. All right. So this is fantastic, right? Because you can see here that what we've got is this is now represented in terms of 2 qubits. Because we could write this as, 0, 0, 0, 1, 1, 0, and 1, 1. So 2 qubits can do the same job as 4 integers over here. Sounds like a win-win, but it ain't a win-win. It's a win, mostly lose. So the reason why it's a win, mostly lose is because of the fact that you lose some really important things from this. For example, let's say that I had the input vector 1, 2, 3, 4 as bits, right? I can clone that to my heart's content. I can make 1 billion copies of that without any issue. But if you give me that quantum state vector coming in, you can't clone that from the no cloning theorem. Furthermore, the other thing about this is imagine that I was given copies of that quantum state vector and I wanted to learn what those numbers were coming in. I would require, if they were in general arbitrary real numbers, an infinite number of copies from this side to be able to capture the precise representation of that over here. So this means that because a bit encoding can emulate an amplitude encoding, but an amplitude encoding cannot emulate a bit encoding, the amplitude encoding is a strictly weaker version of the encoding here. Nonetheless, it's disproportionately used in existing quantum machine learning papers because you can cram a lot more into it. The next thing that I'm going to mention is really important is that the distance that we end up getting now between concept. Oh, yes, got a question online.
Hi, yes. Could you please go over again why this is a weaker version of binary, for example?
Why this is a unitary, what?
Why this is a weaker encoding?
Oh, yeah, sure. Let me just go over that. Because if I give you the numbers 1, 2, 3, and 4, then you could make that state no problem, right? You could just go through and use the standard arbitrary state preparation algorithm from Nielsen and Schwang that ends up using 2-dimensional rotations in order to be able to build this. And so you can deterministically end up making this state if you're given the array 1, 2, 3, and 4. But on the other hand, if you're just given copies of that state vector, and I want to learn 1, 2, 3, and 4 from that, then I'd have to do something like quantum state tomography in order to be able to learn all those coefficients. And that scales like order 1 over epsilon, where epsilon is the tolerance that you need in the output. So if you demand doing it with 0 epsilon, That's an infinite number of samples that we would need to go from the amplitude encoding to the bit representation that underlies it. So that's one of the challenges that ends up coming in with this, is that these two encodings, they do different things. And also, I wanted to raise this because of the fact that this means that the quantum analog of a machine learning task is not unique. If you think about each of these different encodings has different pros and different cons. And the complexity of performing a particular task in one encoding could be vastly larger than the other. So that's one of the reasons I wanted to bring it up. Yeah?
Yeah, earlier you mentioned quantum algorithm did not end up with a quantum state, right? But here may be useful if you have some other algorithm achieving some kind of other purpose, and towards the end it produces a quantum state. And then if that process is efficient, then you don't need to clone. You can generate this state and then learn.
Yeah. So actually, one of the things that I was going to say later, if I get around to slide 10 or so, is that you can view many forms of generative quantum machine learning as an attempt to build an approximate cloner. So what you would do in those cases is you would take in an ensemble of related states coming into this generative circuit that you train, and then you basically just try to build a machine that could then create M copies coming out from the N training datum that were thrown in. So yeah, there is actually a very strong link that you can think of. It's about going to Maria's point about thinking about generative tasks as just being something by themselves. But end-to-end, ultimately, of course, you still do have to measure at the end of absolutely everything. But as an intermediate task, yes, I agree, and that's a good way of thinking about it. Any other questions? Yes.
So this 2 equals 4 business, of course, is known in quantum information. It's called superdense coding and teleportation. Does that help here?
Superdense coding, it sort of helps you. I mean, theoretically, what that allows you to do is get a factor of 2 improvement in the amount of information that would be required to send between 2 parties. And you could think about this as providing and teleportation also, you could think of as being protocols that would describe an ideal encoder-decoder pair that you would end up getting for building as something like a quantum autoencoder. So you could envision an ideal autoencoder that takes a quantum state in and outputs a quantum state in the end. If you wanted to do the identity map, that would actually be teleportation in and of itself. So depending on how you want to take a look at it as being a process that moves classical information back and forth, you might be able to get a factor of 2 from quantum superdense encoding optimally. But you can also end up thinking about teleportation as being a protocol that sends information across some kind of a bottleneck, similar to how we'll see with autoencoders in the slides I'll never get to. Yes?
So you mentioned the complexity of learning that state. What's the complexity of preparing that state in it?
Oh, it's awful. In general, if we're looking at preparing an arbitrary pure state, right, the complexity of building an arbitrary pure state is order 2 to the n log 2 to the n divided by epsilon. Okay, so that's using the standard sort of approach that Nielsen and Chuang end up using. It's not 2 to the 2n because we don't care when we're building the arbitrary unitaries about all the columns. We just care about the first one. But still, in general, if you want to build an arbitrary state, this sucks. I'm sorry, what?
2 epsilon approximation.
Yeah, to an epsilon approximation. And that, of course, is one of the key things because obviously there's an uncountably infinite number of functions that we could put in for the input. So you can never specify that with a finite bit string. So that's why we always need some notion of approximate preparation here. However, oh, there was a question? Okay, they got tired. Cool. So the other thing that I should mention is, of course, there are states that can be efficiently prepared coming in. Things like Gaussians. You know, you can use something like the Kitaev-Webb algorithm to be able to prepare that. Of course, anything that comes from a quantum simulation, which again, I'm not going to get to in slide 20, but those can also be used as efficient inputs for this. Yes.
Just to clarify, it's awful from a quantum computing perspective, but it's not awful. I mean, it's linear in the size of the vector, and no machine learning model ever worries about like loading something that's in the size of the features, right? So from a machine learning perspective, this is what people do all the time, right? Linear time in the size of the data.
Yeah.
So just to clarify this, because I feel like often this gets a bit confused.
So you're absolutely right. And it depends on what your goal is, right? This is why I said that coming up with, from a computational perspective, quantum algorithms that give a polynomial speed up over the algorithms that scale with the dimension of the input, it's not actually all that difficult to be able to do in many cases. But getting an exponential improvement in these general worst case things, that's really difficult to be able to do. And thinking about what we mean by this. So the best way potentially to think about this is you could imagine quantum algorithms wanting to, scaling logarithmically in the dimension of the problem would be the ideal way of taking a look at it. And from that perspective, the quantum states that would specify an arbitrary learning algorithm would be exponentially large, and we would like the number of operations that we're doing on it to be logarithmic in that. So it's just a question about which of the two conventions we prefer. To think about it as quantum people, we usually think about it as being exponential in a number of quantum bits that we use to do it. But ML people will think about it as being scaling with a dimension. But yeah, you just kind of got to keep those straight. And unfortunately, there's going to be some tension between the two types of nomenclature. All right, wonderful. And, oh, I should have moved that slide. Moving on. So let me talk about quantum concept classes. So basically, high level, I'm not going to have time to cover this. High level, the basic idea is as follows. What we can do is, if we want to think about classification as a task on a quantum computer, we could envision the following. We could say, okay, I've now got two different sets of data over here. I'll call this concept class C-1 and this concept class C1 over here. And what I'd like to do is I'd like to be able to build I'd like to be able to build an algorithm that's capable of taking an example, say this one over here, let's call it rho, and be able to distinguish it from all of the states that are present in the other concept class. Okay, and I'd like to be able to do this ideally accurately for the majority of the data set. This is what comes up with the notion of pack learning, which is one of the best ways I feel in order to be able to talk about these types of classification tasks. The idea basically is that what you say is you'd like to build a classifier that's probably approximately correct, which sounds really vague, but it's actually got a very specific meaning. What it ends up meaning is for all but a 1 minus delta fraction of the inputs that you end up getting in, your probability of misclassifying the data from C1 and C-1 is going to be at most epsilon. Okay? So this is really how we could think about a standard discrimination task. And so, if we take a look at the standard thing over here, we could say, all right, well, the standard quantum states that you'd like to be able to distinguish might be things like this. And by the way, do you know why these states are so important for machine learning? They're cat states. Ah, yes. I love basking in your adoration. Thank you for justifying me. So that's basically the whole idea behind it. Now, a problem that ends up coming in with this is that, in general, quantum concept classes cannot be distinguished perfectly in one shot, unlike concept classes in a binary encoding. So I've drawn here two different concept classes coming out, and we can see that these two concepts are linearly separable, meaning I could just draw a line between these two sides, right? And then determine which side of the line the various pieces of data are on in order to unambiguously determine it. So if I had a perfect description of absolutely everything, then I would be able to actually figure out deterministically whether or not a particular vector coming in is in -1 or in 1. But there's a big problem, because even if there's a finite separation between them, these two things may be order 2 to the n distance apart. where the distance measure that I've taken a look at here is the trace distance, which is the analog of the total variational distance for probability distributions. Okay? So if it's exponentially far apart, does anybody see what the problem would be practically with this?
Any imperfection.
I'm sorry?
Any imperfection with like.
Yeah, well, basically what it is it's just like finding the bias of a coin, right? If I wanted to be able to distinguish between a probability distribution, 1/2 minus 1 over 2 to the n, and 1/2 plus 1 over 2 to the n, versus 1/2, 1/2, I'm going to need an exponentially large number of samples to be able to distinguish them. And in fact, actually, the number of samples that you need is related to the total variational distance between the two distributions, or in a quantum setting, the trace distance between the two distributions. So this ends up meaning that if your distance, even in this case, where theoretically you can deterministically separate these two pieces of data, if the data is represented as quantum state vectors, we might actually need an exponentially large number of samples to be able to distinguish them. And so this places some limitations on our ability to be able to do this. And the Holevo-Hellstrom bound specifically says that in this case, we would end up needing, best case scenario, an exponentially large number of examples to be able to distinguish with probability greater than or equal to 2/3. Okay? So that is one of the major bummers and something you've got to keep in mind with quantum machine learning, which is the distance geometrically between the states that you're taking a look at really, really, really matters for determining whether or not your algorithm is going to be efficient in the end. Okay. Now, going to Maria's question, right? All of this stuff over here is really kind of more pegged at looking at discriminative tasks. But generative tasks are also really quite important. So what do I mean by a generative task? I mean the exact same sort of thing, but we can view this as a subroutine that you would carry out in a larger quantum machine learning algorithm. And a subroutine, now, instead of outputting a bit string, saying whether you're in class -1 or class 1, now is outputting a quantum state itself. Obviously, we need to measure it in order to be able to get some information out of this, but we can still view this as a useful subroutine for larger things. And so that's the basic things. And the objective that we're interested in is finding typically something like some expectation value over the set of all density operators that we're putting into our generative learning algorithm for the distance between the output of the channel that ends up generating this and the classifier, or sorry, the process that ends up making it. And yeah, and this probably should just be rho. Okay, now, as I said before, this is actually very strongly related to the concept of approximate state cloning, because theoretically, if we wanted to be able to build a generator for this, one of the things that we can use to place limitations on the quality of the generator that we're building is the no cloning theorem. And one statement for the limitation of this is an N to M cloner over here. And this ends up giving you an expression for the optimal fidelity that you can end up getting with the input to output pairs as a function of the number of copies that you end up putting in. And so this is a case where you have N copies coming in and M coming out. So what this ends up saying is that if we want to have a truly large number of states coming out with a high fidelity, then we're going to need a very large number of training vectors coming in order to be able to do this. So this places some limitations on the size of the data set that you're going to need in order to be able to actually train a generator, because no matter what you end up taking a look at, you cannot beat this lower bound on the fidelity of the outputs. So I wanted to raise this because there are actually limitations that we already know from quantum information theory about the performance of these generative tasks. Okay, and I don't have time for Taylor's version of quantum generative training. I really wanted to use that because I do a lot of things involving Taylor's theorem. And so I really want to call it like, Taylor's version of HHL, but anyways. What am I talking about here? Boring. Oh yeah, this isn't boring. Okay, so 15 including questions. Wow, okay, I am never going to get there. So basically, what I want to talk...
Wait. No, it's 15 total, right?
With questions, with questions.
Yeah, 50 with questions.
Yeah, the breaks in 15 minutes.
Oh,
No matter what.
okay, good.
All right, cool. So I want to talk about another type of a problem that I think is really, really quite important, which is using ideas from quantum machine learning essentially in order to be able to learn things about quantum systems in and of themselves. So frequently, people end up looking at this inside the context of Hamiltonian learning. So the idea basically is that with Hamiltonian learning, what we've got is we've got something like the following. We've got some physical process. So our channel will map we've got some channel that will map for a specified time and density matrix. It will apply a evolution of a hidden Hamiltonian to this state. And what our task is now is to be able to learn from training examples what the Hamiltonian actually is. So this is actually a really important task. Experimentalists do this all the time when they're trying to figure out, well, what system do they actually have and how do they build good controls in order to be able to manipulate it? You've got to understand, as Juvens would say, knowledge is the root of power. Sorry, it's probably too geeky for almost everybody here. But in any case, the basic thing is that these tasks also fall inside the edifice of quantum machine learning, even if the thing that ends up coming out of it is actually a classical model here. Because what we want at the end of the day is we would like to have a description of that Hamiltonian given as a bit string. We don't necessarily need to build a model that directly generates it, but we just need a specification of it. Okay? And there's, a bunch of different ways that we can think about it, but really fundamentally what we would like to be able to do is we would like to be able to find a set of model parameters that specify our Hamiltonian over here. So we can imagine that as being something like sum over j, theta j, hj, where hj is maybe from a set of Pauli operators, or some nice operator basis like that. And we would like to be able to figure out the theta j's such that the distance between the predicted states that we generate from this and the observed states is minimized. And one of the great tools that's come up over the last few years from this is this idea called shadow tomography, which ends up providing us a wonderful way that we can end up building classical models for states. And that is perhaps the dominant theoretical tool that's used these days in order to be able to get an idea about A, what your state is, and then from that state, you can figure out, say, what the generator is. To give an idea about this, and shamelessly plug work that my student and I did, if you know, second thing about me, first thing is I never show up to conferences. Second thing is that I will shamelessly plug all my students' work. But this is the basic idea behind this is that what we can do is we can end up actually coming up with a transformation that embeds the Hamiltonian that we have through simulation inside a quantum state itself. Then once you've done such a transformation, what you can do is you can build a model for that quantum state, a classical model, that will predict all the measurement outcomes you want in a PAC setting, so with some probability of failure and with some accuracy when you succeed. It will tell you what the expectation values of this are. And from those expectation values, we can work backwards and figure out what the Hamiltonian is, because the Hamiltonian is embedded in the state. So this approach over here is kind of similar to earlier work that was done looking at Gibbs state learning for this, except here what we do is we use a pure state in order to be able to encode the information, and it scales very well with the parameters. But in any case, this would be an example of some task that is within quantum machine learning that actually just requires us to output a classical understanding about it. So from this perspective, you can actually end up viewing quantum machine learning is actually encompassing a good chunk of what people experimentally would do anyways. Yeah, Srini.
Are you just given copies of that, or can you make queries as well?
Yeah, so basically, it depends on which of the two models we're taking a look at. So fundamentally, at the kind of the highest level, you could envision making queries to this, an oracle that yields copies of this particular state. But we can end up using tricks basically we need a controlled Hamiltonian evolution, but from that we can actually build the logarithm of the Hamiltonian and embed that inside of a state to turn queries, controlled queries, to ordinary Hamiltonian evolutions into queries to this state. And that's one of the reasons why a T shows up in the final theorem down at the bottom, because if you have a sufficiently short evolution for the queries to the evolution oracle, you'll need more copies of those to be able to build that state. Any other questions? Yeah, Rob.
What's the output metric in this theorem for? Like, what does error epsilon mean?
Okay, so error epsilon ends up meaning here this is a good point because actually you get different scaling depending on the error. We took the Euclidean norm of the error in the Hamiltonian parameters that we've learned for the output versus the true parameters. If you take a look at the infinity norm, you'll end up actually getting much nicer looking scaling. So the yeah, that's an example of this. Oh man, I really don't have time here. What's something that's kind of cool? That's boring. That's kind of important. Oh, that's really important. Ooh, that's stupidly important. Okay. No! All right, let's deal with the question.
Sorry, I have a question. Why you didn't mention the angle encoding?
Why did I mention the angles?
Angle encoding.
Oh, the angle encoding. Because I just view it as a particular parameterization of an amplitude encoding.
Okay, thanks.
Any other questions? All right, great, good, because you don't have time for questions. So I want to just mention this one major problem, because this is a vitally important challenge, which is actually, generically speaking, a problem that we end up running into is that these quantum models that we end up taking a look at are often trained using gradient descent on a particular objective function. And the reason why this is important is because of that slide. Remember I told you ages ago that I had a slide that I put in the wrong spot? Now we get to go back to it. So gradient descent, how it ends up working is that if we have a loss landscape that ends up looking like the following, it's really flat for a long time, and then all of a sudden starts making some huge progress. You run into a major problem because the size of the step that you're going to end up needing for it will have to be set up in such a way so that it doesn't do something horribly wrong when it ends up taking a step. So in order to have a reliable gradient descent algorithm that could run into these things along the way, you have to have a very small learning rate in order to be able to deal with this properly. But if you're dealing with this kind of a flat landscape at the top, then you of course need a huge learning rate in order to be able to make progress. And this tension between these two things that you end up needing creates this, this issue, where if you have very small gradients, you'll need a very large number of quantum operations. Fortunately, gradients aren't generically small, are they? Yeah, I wish. And that's what these barren plateau results end up saying. Barren plateaus, there's many different types that I was going to talk about, but I totally can't. It basically ends up saying that generically, if you end up modeling the states that are produced by your model as being har random, then the sizes of the gradient that you end up expecting is actually going to be exponentially small. And you can end up saying that there's a concentration of measure, meaning for all but an exponentially small fraction of such randomly chosen inputs, your gradients are going to be exponentially small, which means you're totally hosed when it comes to this generically. And so this notion of barren plateaus is a fundamental thing that needs to be studied in order to understand the asymptotic viability of particular approaches to machine learning. Not all of them necessarily will have barren plateau problems, meaning in the asymptotic limit it's provably exponentially small, but vanishing gradients, even if it doesn't have a barren plateau, could come up. Yes, Lynn?
So this just shows that there's a long region where it is very flat. Does it also predict somewhere the gradient will be very steep?
So what it actually ends up predicting is that if you start with a random initialization for your model, then with high probability over those random initializations, if you're using this HAR model for what a random initialization ends up meaning, the value of the objective function is going to be basically crap, and the gradient is going to be crap.
That's the small part. What about the big part? You had the picture. Does it also predict?
Unfortunately, no. These results don't necessarily predict anything about that.
How do you know it's a plateau?
The big problem, though, that you run into is figuring out in the quantum setting what direction to move in. Because if you want to be able to figure out the gradient by sampling, right, and it's exponentially small, we'll need exponentially many quantum samples in order to be able to make sure we're moving in the right direction. If we knew what direction to move in, then we could choose a huge learning rate and compensate for this problem. But in a quantum setting, we don't.
But is there evidence there is actually something going on?
No, there is no evidence.
If you were to follow the route to the optimal thing somehow by a miracle, that's how it would have to look like, right? I don't know, because you're at zero at the end.
Yeah, this doesn't make an argument specifically about the path that you would take through the optimization procedure, because as soon as you take one step along the optimization route, you're no longer at a typical point with respect to the Haar measure. So that's one of the big challenges that ends up coming.
Why? Because it's important. Like, why is the average value of the gradient so important?
Well, because the reason why the average is it's just saying typically.
No, I know what it means, but it's just like, I mean, that's not the genetic situation you face, right? I mean, you could be in a point where the gradient is just.
And what I was saying is that this is where one of the things ends up coming in for this, is that this is a model for what will typically end up happening. Now, for an application like quantum chemistry, the initial configurations that you begin in are usually like a mean field approximation to it, which is not a typical configuration. Similarly, actually, older methods for classical machine learning, such as the Boltzmann machine, would actually often begin with a mean field approximation to what the weight should be for the network, in which case you would also not be starting off in a typical configuration. So there are caveats and ways that you could get around these limitations, but it's important for us to understand that we cannot expect a quantum machine learning model just begin with an arbitrary initialization and have it perform well. Okay? So there's other methods. Some generative models don't have barren plateaus, and they're cool, but I don't have time to cover them. And you can sometimes evaluate their gradient in polynomial time, which is cool, but I don't have time to cover that. But one of the things that I want to talk about last is what is something kind of positive that we could end up doing. So something positive that we could end up doing is, a question is, like, what kind of a task could I think about that might be potentially valuable and likely ends up leading to some kind of an exponential advantage? So here's just a brief example of such a task. The idea basically is, what we do is we feed in a series of nuclear positions into our system. And what our task is to output an approximation to the ground state, not the ground state energy, the ground state of that of that electronic system at those fixed nuclear positions that are put in. So the idea basically is that what we do is we give a set of copies of the following type of training data. We have a series of positions for the nuclei, and I'll give you a copy of the corresponding ground state at each of these positions. And we'll, our training data is input in this particular form. Then what I'd like to be able to do is I'd like to be able to build a generator that will take an arbitrary set of xi's coming in and predict what the rho I corresponding to that would end up being. Okay? So that's the general task, and the question is, how could you do it? So the way that we end up doing it is we use the following, which some people refer to as a feed-forward quantum neural network, but I think that's an awful name and should be killed immediately. But nonetheless, I'm kind of stuck with it. So basically what you have is you have a series of these parameters over here. What we do is we build an ordinary neural network that takes the xi coming in. Then it will generate a series of theta i's that then end up getting fed into this circuit down here, which is fed in 0, and it will output rho I down at the bottom. So this is an example of a kind of a hybrid algorithm in one way. What we do is we take in the positions, and then we generate the corresponding quantum states coming out for it, and we evaluate our loss to be the average quantum relative entropy of the input versus the output states over the training set, and then let it run on it. Question is, how well does this end up working? And shockingly, really good. When we took a look at hydrogen chains as well as small molecules with this, with only 4 or 5 training examples for this, we ended up getting fidelities that exceeded 99% and ground state energies that were extremely close, even though we actually weren't technically training on either one of those metrics. So this is an example of kind of a cool task that if you're looking at generating copies of ground states, which is something that you want to do in many chemical applications, quantum machine learning could speed it up tremendously. And you can do the same thing with thermal states and stuff. But okay, that's it. And I didn't have a conclusion slide. Wow, that is so me. Okay, so to conclude, what is quantum machine learning? Well, quantum machine learning really is just a process that ends up yielding algorithms where the output of the algorithm ends up depending on a set of quantum states that you train it with. That's it. There's generative tasks, there's discriminative tasks. We can think about all of these, but at a high level, the thing that I really kind of want to get across is that we're still actually struggling with the conceptual era of this field. We don't really know always what the right analogs are for various machine learning tasks. And sometimes the direct copying of ideas, even fundamental ideas like backpropagation, over to the quantum setting, actually don't end up yielding necessarily big improvements or any improvements because the concepts are so different that we want to do here. And I really strongly encourage that, when approaching quantum machine learning, you ask, okay, not just what the right quantum analog is for a classical task. Often, actually, the better question is to ask, what's the right classical analog for a quantum algorithm? And I feel with that, we can begin to actually really begin to understand full breadth and width of what's possible for learning tasks in a physical world. Thank you.